Let's see what we mean by the expression saying that Laplace transform is a linear transform. So first, let's consider a linear combination of functions. And what I mean by that mathematically is that going from 0 to infinity, we have an alpha f of t, where alpha is a constant, plus beta g of t is all multiplied by e to the minus st dt. We can factor out the alpha since it's not a function of time, as well as beta. So now we have 0 to infinity f of t e to the minus st dt plus beta g of t e to the minus st dt. But this, by definition, is f of s, and this, by definition, is g of s. Hence, we can write the Laplace transform of alpha f of t plus beta g of t as equal to alpha f of s plus beta g of s. So this expression here is what we mean by a linear transform. So a linear combination of functions, and you take the Laplace transform, turns out to be the linear combination of its Laplace transform. And we'll see some examples on how we apply this concept of a linear transform associated with the Laplace transform. So for example, earlier we found that the Laplace transform of 1 is equal to 1 over s, and the Laplace transform of a ramp, we'll say 5t, is equal to 5 over s squared. Well, the Laplace transform of a combination of these, let's say 1 plus 5t, is just simply the Laplace transform of each. So it's 1 over s plus 5 over s squared. Another example illustrating the concept of linearity is earlier we have the Laplace transform of 4 e to the minus 3t, which is simply 4 over s plus 3. And the Laplace transform of minus 10 sine of 2t is simply minus 10 times the sine of this, which is equal to 2 over s squared plus 2 squared, or 4. In this case, we have the Laplace transform of 4 e to the minus 3t minus 10 sine of 2t, which is equal to 4 over s plus 3 minus 20 over s squared plus 4. So that illustrates the concept of linear transform using these examples. Now that we did several examples of some Laplace transforms, let's generalize some of the results that we discovered earlier. So here we have the Laplace transform of constant. We saw that it was 1 over s. Then we did one for a ramp, and we saw that it was 1 over s squared. We can generalize this as t to the nth power. The Laplace transform for that is equal to n factorial over Sn plus 1. Here we have the Laplace transform of an exponential, and we saw that it was 1 over s minus a. Laplace transform of a sine kt is simply k divided by s squared plus k squared. For the Laplace transform of kt, s it's equal to s divided by s squared plus k squared. The hyperbolic sine kt is equal to k divided by s squared minus k squared, and the hyperbolic cosine, its Laplace transform, is s divided by s squared minus kt. So these are some of the basic Laplace transform of some basic functions. So let's find the Laplace transform of a piecewise continuous function shown here, where f of t is equal to 0 from 0 to 3 and 2 when t is greater than or equal to 3. And graphically is shown right here. Where it's 0 from 0 to 3 and 2 greater than 3. Since this function is divided into two parts, we'll do the Laplace transform in two parts, and then you recall the Laplace transform of f of t is equal to the integral from 0 to infinity f of t e to the minus st dt. Now we're going to have two integrals, one from 0 to 3, that's 0 e to the minus st dt. So this one goes to 0, plus from 3 to infinity 2 e to the minus st dt, since the value is 2 greater than or equal to 3. When you complete this integral, we have simply negative 2 over s e to the minus st with an upper limit of infinity and a lower limit of 0. Well, the upper limit for this is 0 when you substitute infinity in this expression, minus 2 over s e to the minus 3t. And completing this is just 2 over s e to the minus 3t for s greater than 0. So that's the result of this expression of the Laplace transform of a piecewise function.